introduction.
Okay, over to you, Regina.
Okay. Yeah, thanks a lot, Sam, for the introduction. We as AIT are working since quite some time already on the topic of flexibility, so I'm also very happy that we can share our results today and discuss it with you about the evaluation of the real-world EV and heat pump flexibility potential. So what's on our agenda today? So we'll first quickly introduce the project, then shortly talk about what is flexibility and where can it be used for. Then we will present our high-level model, its application and results, and Viktoria will talk about the heat pump flexibility potential and Ben about the EV flexibility. And then we will conclude with some policy recommendations and research gaps. Then I will hand back to Sam to talk shortly about the users TCP, and then we will have the Q&A, as already mentioned. So what was our project about? Our project was about the interpretation, application, and evaluation of a proposed generic model for calculating flexibility potentials of behind-the-meter electric appliances. And we applied our model and tested it on heat pumps and EVs for the country of Austria. And the goal is to have a model to evaluate the real-world flexibility potential for a certain region or country. What is flexibility in the context of a project? I will illustrate it quickly here with this example. So this is the illustration of a heat pump operational profile. The black bold line is the normal operation, which it's the set point the heat pump operates to keep the temperature at a certain room temperature level, which is the black dotted line, and the flexibility activation is a deviation from this profile. So if the heat pump consumes more electricity, for instance, for a certain amount of time, the room temperature will rise, which is the orange dotted line, until it reaches some upper limit, which is a restriction, for instance, by the user. And then the flexibility activation ends, and the heat pump can operate at its normal level for the rest of the time. And of course, to enable another flexibility activation, some catch-up effects would be needed to decrease the temperature again, but they are not shown in this figure here. So the flexibility here is the orange area, which is the deviation of an operational profile. The deviation from a baseline is the flexibility potential. And where can we use this flexibility? So of course, we can use it to use price differences at day-ahead and intraday spot markets to buy electricity when it's cheap and consume less when it's very expensive. But it's also possible to offer the flexibility for different balancing and system services, for instance, balancing reserve or redispatch congestion management, or also use it for imbalance settlement. And for these specific products, the requirements are more strict to participate than at the spot markets. But it's also a very important use case for flexibility. And then there are also non-market-based use cases, such as peak shaving, for instance, if the grid access is limited, or just to increase self-consumption or reduce power peaks. And then there the revenue streams come from reduced grid charges, for instance. So there are a lot of different possibilities to apply flexibility. So it's going to be very important, especially in the future. For our project, because the flexibility can differ a lot depending on the environmental parameters, for instance, depending on the outdoor temperature, the flexibility of a heat pump is different in summer than in winter. And it's also different depending on the height of flexibility activated. If I activate less flexibility, it can be activated longer. But to simplify it for our project, and since also the focus is a lot on the social, regulatory, and behavioral parameters, the assumption for the technical potential is the maximum activation possible for around 3 to 4 hours, assuming an average load factor. And this is an overview of our high-level model. So to derive the flexibility potential for a country or a region, we start with a number of total products, which is then narrowed down the number of capable products, and only a share of these capable products are really enabled by users. And this number is multiplied with an average product flexibility, which is derived from an initial technical product flexibility, which is the installed power, and then it's reduced by environmental factors and also by user behavior. And yeah, these steps or these parameters are influenced by different influencing factors, which could be financial, behavioral, or technical. And these influencing factors can be impacted by different regulatory policy measures and instruments, which we also investigated. And now I will hand over to Viktoria to explain our model for heat pumps.
Thank you, Regina. So let's dive into applying the model. Let's start with the number of assets. The number of total assets is dependent on on technical, financial, and behavioral factors. So first of all, what heat pumps are even available in the market and what alternative options for heat supply are there. Then, of course, what does it cost to install the heat pump and what is the energy pricing of operating it? Behavioral factors influencing the total number is the hassle factor, for example. It describes the effort that it takes to select a heat pump or and to let it be implemented. On the other hand, there is a peer effect or knowledge spillover effect, meaning that if your neighbor has a heat pump, you might be more willing to adopt one yourself. The biggest barrier of using a heat pump is user concern of the reliable performance of heat pumps. Then your heat pump might not be capable of being externally controlled. That's a technical factor. For data for Austria, since 2005, the heat pumps usually are externally controllable, and since 2015, they even have smart grid interfaces. If they do not have the respective interfaces, you might need to do a retrofit, which is a financial factor. Then the last point is financial and behavioral, and I will discuss it in more detail because here our users come into play and they enable or do not enable the heat pump. Then let's look at the flexibility part. The installed power is dependent on technical factors. That's what kind of heat pump do you have and what are the activation times and ramps. Then where is the heat pump applied? So what is the situation? What is the source temperature, first of all, and an environmental factor? The heat pump will need a different power to supply the same amount of heat operated at different source temperatures. Then there is the heating demand, also dependent on the building type, but also on behavioral factors. And is there storage available, which also means you can only switch on a heat pump if you can load a storage or supply the heat demand that you currently have, or maybe preheat your building. On the other hand, you can only switch it off if it's currently running and currently supplying heat demand or filling up a storage. Technical factors would be capacity and duration, which are not independent of each other. So if you want to have a longer activation event, you would need to scale down the capacity, or if you want to have a high capacity, you can only do it for a short amount of time. And another technical influencing factor is the availability of the communication network. And in the last step, from situation to the actual available asset flexibility, the user comes into play again, and we will discuss it in more detail. Good, let's start with looking at the enabled assets. We have behavioral influencing factors, most importantly, the consumer general openness to provide demand response. So meaning, do they allow external control? I brought with me some numbers. For example, for Germany, external control is off limits for a quarter of the participants of this survey. Or in Poland, maybe more on the bright side, 84% have a general openness to participate, but if they get tangible benefits or savings. So that brings me to financial influencing factors. There's some more data from the US. Social learning is a big part in the willingness of users. There is data from Portugal suggesting that social learning significantly influences the demand response acceptance. For financial influencing factors, there's a wide range of a yearly revenue that users will expect. For example, for the US, it's between $10 and $50, and for Finland, it's 200 euros per year. For flexibility, let's look at the behavioral and financial influencing factors. So first of all, the height of the allowed temperature deviation influences the flexibility to a high degree. So if I'm in my building and I have set a comfort temperature, how much will I allow the heat pump to either preheat the building or let it cool down? For users, the duration of the activation and the frequency of those activations are not independent, so they might allow more events if they take shorter or less if they take longer. So there is data from Switzerland suggesting that once a day, it's okay to do it for 30 minutes, but if you want to have 3 hours, they would only allow it 20 times per year. Users also want to know in advance, some 24 hours, some even up to 1 week. If the discomfort is too high for users, they always have the option to override the activation. And we have some data from the US and Canada here for air conditioning, but there's an average override rate of 13% of events. And the range of these this is quite wide. Just the average is at 13%. For financial influencing factors, there's not a lot of quantitative data, but you could generally say that the more lucrative or visible the program, the more likely the user will stay enrolled and not override the activation. I would like to show you some numbers for an example. So Austria in 2030. This is a conservative case, meaning that I took a moderate forecast for the total number of assets. And in all other cases, taking the influencing factors into account, it's a conservative case. Let's start at the total number of assets, which is 850,000. We lose some at capable assets and arrive at 800,000 capable heat pumps that could provide flexibility. And then we lose 70% at the users. And that leaves us with 240,000 heat pumps that are capable and enabled by the users to provide flexibility. The average technical asset flexibility is 1,560 watt per heat pump. This is the installed power. Now, if we look at the situation, we already have to distinct between positive and negative flexibility. And we arrive at 860 and 700 watt per heat pump. We lose at the users, again, 35%, leaving us with 560 and 450 watt per heat pump for positive and negative flexibility. Now, if we multiply these two numbers with each other, we get a flexibility potential that is 135 megawatt for positive flexibility and 110 megawatt for negative flexibility. And now, where do we start with policy measures that will be shown by Regina a little bit later? We cannot do anything about the technical and environmental influencing factors, but we can do something about the users. So the green highlighted numbers, these we can influence to increase the flexibility potential. Now I would like to show you a trend over time from 2020 to 2030 for a conservative and an optimistic scenario. Let's first look at the flexibility potential. So in the diagram in dark blue, you could see the technical product flexibility. Then we lose quite some capacity in the specific situation, and then again lose some at the users. And the difference you can see between the diagrams is basically the users. On top, you can see the number of heat pumps. Again, in dark blue, the starting point, the total number of assets, which is similar in both cases, but not the same. Then we lose a tiny bit that's not capable of being externally controlled, but the majority of heat pumps will lose at the users. If we multiply, we get the numbers that I showed earlier for 2030 on the left side for the conservative scenario. And for the optimistic scenario, we arrive at 650 and 520 megawatt for positive and negative flexibility potential in the year 2030. And with this, I hand over to Bill.
Okay, so I will talk about the flexibility provision by electric vehicles. On the next slide, we will see that the overall high-level model is quite similar, which with some differences. First of all, we consider here two different components or products. We have EVs on the one hand and chargers on the other hand. And only in combination, they will be able to provide flexibility. And the second thing as a side note is that we are rather focusing on home chargers because we believe that they are contributing to the flexibility the most. Because if you are using a public charger, you are more interested in charging up your EV than providing flexibility in the short time. Okay, the next slide, please. Then we will go through each of the components a little bit. So the first one, we will look at the total number of products. On the next slide, we see here that we are considering some major points when it comes to estimating the number of EVs. First of all, of course, what are the costs for the EV? We have some subsidies when buying EVs. Subsidies will run out, for example, like in the US. This is normal because in the near future, for example, 2027, we expect that the EVs will be cheaper than conventional cars in the same category and performance, of course. And by then, we don't really need subsidies anymore. The second point is the charging infrastructure availability, because if you have a home charger, you are more likely to buy an EV than if you don't have a home charger. And by subsidizing home chargers, you can also increase the number of EVs. Then, of course, the third point is the costs of the fuel versus the cost of the electricity. So if the electricity is much cheaper than the fuel cost, then you are more likely to buy EVs. Okay, thank you. Next one. So now we are going from the number of total products to the number of capable products. And for this point, what we are considering here on the next slide is that we are looking mainly on the chargers. Next slide. Yeah, thank you. So here, as mentioned earlier, we are mostly focusing on the home chargers because you are parking your car mostly at home and for the long period of time. This is where the flexibility provision can make a big change into the grid system. So for the home chargers, the first requirement is that you need a private parking space. And in Austria, it's around 86% of the households which own a private parking space. So this is an upper limit, let's say. And then from different studies in the Canada and US, we see that if the home chargers are subsidized, then people are more likely to install home chargers at home. Okay, next one. Then in this step, we are looking at the number of enabled products. So they are capable, but what makes them enabled is the user. Next slide, please. Here we see that it mainly comes to the financial benefits if people are generally willing to provide flexibility with their EVs or not. For example, we can offer users a cheaper electricity, so euro or dollar per kilowatt hour. If this rate is reduced, then people will more likely to provide their EV as a flexibility product. Or you can also just pay them 100 US dollar, and they will be more likely than not willing to provide the flexibility with the system. So this is the user aspect. Now we are looking at the technical product themselves. So those are the limiting factors by hardware. For example, if we are talking about the home chargers, they are limited by 7 kilowatt. This is the standard average household home charger capacity when it comes to power. And the energy flexibility depends on the battery capacity. Nowadays, it's around 54 kilowatt hours, which the vehicles can store. And here, what we want to say is that regulatory measures, they don't have a direct influence, but they are more technology-driven or market-driven, like the battery capacity. So next one. And from the technical product flexibility to situational product flexibility, at this point, we are looking into the mobility, behavior, and the technical aspects. So in Austria, by our large survey, we can see that the average person moves around 34 kilometers per day. And among that, 19.5 kilometers are covered by the car. And if we have these numbers, we know that the average daily consumption is around 2.8 kilowatt hours. Of course, we also have to take into account that the EV is also consuming some electricity, even if it's parked. But let's say roughly 3 kilowatt hours. And this one translates a little bit into the asymmetric flexibility because we have more positive power flexibility than the negative one, because the car is more likely to charge what it is consuming per day. So therefore, we have 7 kilowatt to minus 6.7 kilowatt when it comes to power flexibility. And in terms of energy flexibility, we are considering that people will likely want to have at least 50% of their state of charge, and they don't want to charge it above 80%, not to damage the battery. So this range, like 30%, this is the average energy flexibility an EV can provide. So next one. And the last one is when we are going from situational product flexibility to average product flexibility, which means we have all the technical aspects together. But now the last step is how are people dealing with it? Then let's look at this. So what are the obstacles? I mean, you can have an EV, you can have your own home charger, but it doesn't contribute to the flexibility if the EV is not connected to the grid. So therefore, what are the aspects why people are not plugging in their EVs? So here we have two main factors. First of all, we have a hassle factor, because nowadays it's just the beginning of the EVs. You need to connect them via this charger, the wire, which is rather complicated, I would say. And you want to do that without a reason. Compared to that, maybe in the future, we have some charging pads where we have the integrated charging facility into your parking lot. And then if the parked car is at the right place, it will have some flexibility provision if the user is willing to. And the next thing is users might fear, when we are thinking about vehicle to grid usage, that the battery is not charging but discharging, and therefore they are fearing that they don't have the enough range on the next day in their EVs. So there's some fear of range. And the second fear is that if they are charging and discharging the battery too often, they will degrade their battery. So those are the negative aspects which might hinder people from providing the flexibility. But on this aspect, we don't really have a lot of data right now. Okay, next one. So similar to the heat pump, let's look at some numbers. So on the top, we have an estimation about the number of products. We will have more than 600,000 EVs by the year 2030. And then let's say a share of them, they don't have access to home chargers. And the last one is the number of people who are willing to provide flexibility in general. And on the left side, we say this is maybe 20%, and on the right side, in the optimistic scenario, maybe 50%. This depends on the subsidies or incentives. And on the lower side, we have the average product flexibility, which we assume that it will remain constant when we are looking at the power flexibility at 7 kilowatt for the home chargers. And in combination, they will make up the power flexibility. And on this slide, we see the energy flexibility. The top is the same with the number of EVs. And on the lower side of the slide, we have two different estimates, namely if the battery will increase in their size until 2030 or not. On the left side, we have a conservative scenario where we say that it will remain constant because more and more smaller, cheaper EVs are coming to the market. And on the right, we say that we have the optimistic scenario where the battery will grow in the near future. And then we will end up with more energy flexibility in total. Okay, then the next one. Yeah, the main difference here on the top is if users are willing to provide flexibility in general, which is dependent on the incentives. And on the lower side, so the next slide, As I mentioned earlier, this is the difference where we ask ourselves, will the battery size of the EVs increase or not? And I think those are the final things. Yeah. Thank you. I will give back to Regina.
Yeah, thanks a lot. Yeah, I will conclude with a short glimpse into the research gaps and policy recommendations. So you've seen already. Sorry, now. This slide from the heat pumps. So I just want to repeat that the most part of flexibility gets lost due to the uses here. So we have quite some high numbers here, with minus 70% and minus 35% in the conservative scenario. That's what we found in literature. And also for the electric vehicles, the step from the number of capable products to the number of enabled products is quite high, what we found from our research. And what we also found, because we read quite a lot of literature, that there are also research gaps on the policy instruments that are influencing the willingness of users. So there are possible policy instruments named, but the quantitative effect is not very well researched. That was what our finding was, or our feeling when reading the literature. And we did this overview of policy recommendations. So there are quite a few. We separated them by influence types, if it's a regulatory, a financial, social, or technical, or behavioral, if it's influencing this, or if it has an impact of this influence type, and if it's a direct or an indirect mechanism, and then a qualitative description of the impact, and of course the policy measure itself. Yeah, and the influence parameter. So there are policy measures that are influencing the number of installed total assets. There are policy measures that are influencing the number of capable assets, and that's where we lose the most, the influence on the number of use, participation, and behavior. So policy measures, for instance, if suppliers or aggregators are enforced to provide more demand-side management programs and variable tariffs, for instance, then the users have a broader range to choose from, and then the acceptability would rise, and the willingness of users as well, or might rise. And what's also in our opinion very important are training programs for heat pump installers or also home charger installers, because yeah, if the people can talk with professionals directly, then it also enhances the trust. And it's also important that the installers, of course, know about flexible components in the future, and certification schemes for flexible ready products or installers would also be helpful. Yeah, and maybe what's also, of course, always a topic, but it's more a technical thing, is the standardization thing. So to standardize the interfaces and legal requirements for asset interoperability would be a policy measure that could enhance this as well, which we deem important. So our conclusion is that there is extensive data on flexibility and related technologies, but the different studies also seem a bit inconclusive or lack quantitative depth. For instance, as you saw, the difference between the conservative and the optimistic scenario, for instance, about the user willingness to enable their products is quite big. And yeah, and the policy measures are very likely to influence both the number of flexible technologies and also the amount of flexibility they can provide. But it still remains a bit unclear which measures are the most effective ones, and how their specific impacts are. Yeah, then I will come to an end. Thanks a lot.